Assalamualaikum dan salam sejahtera. Alright, today we will continue on the next topic, which is heat exchanger. Alright, this topic cover introduction, type of heat exchanger, overall heat transfer coefficient, Fouling factor, log mean temperature difference, calculation of heat exchanger size, effectiveness NTU method, compact heat exchanger, and the last one, design consideration. Okay, basically there are two types of heat exchanger. The first one is A, parallel flow. Second one is B, counter flow. Parallel flow and counter flow, the different are, for example, here you could see the hot in and the cool in is in parallel. Okay, is go in parallel direction, and then they are going out. Okay, for the other one, counter flow means that the hot fluid is going on right direction, and meanwhile the cool fluid is going on left direction. Okay, this is counter flow. If, for example, we try to sketch this graph, we could have the graph of counter flow. It start at very big difference and end up to some points in very small differences. Okay, so maybe if we make it this one a bit longer, so it will end up at one point. Meanwhile, on the other one, the cool and the hot fluids is drawn in different way because you have because it's counter flow. So you could see that the difference between the hot and the cool actually is, I'm not sure whether it's the same. Yeah, it's actually a big difference compared to the parallel flow. Okay, here you could see another type of flow, but not usual being discussed. This one is cross flow. Okay, in a compact heat exchanger, two fluids usually move perpendicular to each other. The cross flow is further classified as unmixed and mixed flow. So unmixed, this one is unmixed because it have a fin. So when the air is going in that directions, the air will not mix with each other. And the other one is if the air is going here, so maybe the air could go up and down and up and down, so the air is mixed with one another. We have here a compact heat exchanger. This is an example of compact heat exchanger where the area density is bigger than 700 meter square per meter cube. It's being classified as being compact. Next one, this is shell in tube heat exchanger. This is the most heat exchanger in industry, the one that we use for example in aircon. You could see we have one in HVAC industrial lab. Okay, here this is the middle one is tube. Okay, QR code, color this one, and the middle one is tube. So these are the tube, and we have the outer one is the shell. Okay, these are the shell. Alright, later on we will see how shelling tube heat exchanger functioning. Okay, over here you could see there are another different of heat exchanger. For example, we have regenerative heat exchanger, involve alternative passage of hot and cold fluid stream through the same flow area. And we have another one is dynamic type of regenerator. Then we have a condenser, and last one we have a boiler. This is an example of heat exchanger. Alright, for example, over here we have a multi-pass flow arrangement in shelling tube with heat exchanger. This one we have one shell path and two tube path. Okay, for the one shell path is because of the these are the paths that the flow of the fluid through the shell. Okay, another one we have two tube paths because of this fluid is coming in and then going back and out. So this is first path and this is second path. Okay, another one we have two shell passes and four tube passes. So for the shell, these are the first one, the fluid coming in. The fluid could be water or refrigerant, for example. And this one is second path. Go first towards the left and second towards the right and coming out. And we have another one for tube, four tube passes. So we have this is coming in, going to the left, first one, the second path going to the right, and then turn and going to the left, but they have a barrier over here. So and going to the right and coming out from the heat exchanger. Okay, the next one we have a plate and frame or just plate heat exchanger. We call it plate heat exchanger. So this one is actually a symbol of plate heat exchanger. This is A plate. For example, okay, this is A plate, and then we have a B plate over here, and the A plate. Alright, to further detail regarding this plate heat exchanger, I will post another video regarding this plate heat exchanger. The best or the advantage of plate exchanger is this one is very effective because the plate is being very compact, so it can be stored without large space needed. Okay, the next one we will learn on the overall heat transfer coefficient. It's actually U. Right? So in overall heat exchanger, for example, we have over here heat exchanger involve two flowing fluids separated by solid wall. So we have this one is solid wall. We have a solid wall. So we have a hot water inside, maybe going there, and we have another one is cold water inside, maybe going in the same direction. We're not sure. For example, here we have cold fluid and hot fluid going in the same direction. So in this diagram, the heat is being transferred from inside to outside. Okay, the heat is being transferred from inside, the hot one, the middle towards outside, right? So because it's transferred towards outside, this is directly out of the cold wall, the outer wall. But actually in this case it's only assumed the hot fluid is the hot of the hot fluid is only being transferred to the cold fluid. Okay, hot fluid is being transferred to the cold fluid. So here the first thing is usual, and if you like to find the formula, the very simple way is by drawing this thermal resistance network diagram. Okay, so you have the first one, you have Ti. Ti is the medial temperature of the fluids. Okay, if I would like to draw another one, this is Ti, and then the inner one, and we have the wall. Just draw the wall a bit big, so yeah, we can see the thickness. And then we have another one. This is fluids, not the outer wall, but this is fluid. So the calculation is only up to the fluid. So here we have from the middle temperature, we have a resistance towards the inner wall. This is maybe T1. I'm not sure if you like the T1. And then we have another one, resistance towards T2. And last but not least, this one is put what? This one you put T naught. Okay, T naught. Okay, let's follow the one. Put T naught. So it not yet reach this outer inner wall, but only reach at the middle temperature of the cold fluid. So you have over here Ti, T naught. Okay, because as this one is this one is convection. So you have convection over here. 1 R is equal to 1 over Hi Ai. Then the middle one you have, this is because this is wall is conduction, so R wall equal to R wall equal to, because this is a cylinder, so R wall is equal to this one, ln dO over di over 2 pi kl. Okay, R wall. And then we have last but not least the outer one. So this is outer is still convection, so we have R convection is equal to 1 over H A. In this case we have HO. Okay. And we plus everything, we got our total Ri plus R wall plus RO. We got this formulas. AI, this is to find AI. AI equal to pi dl, and then we have AO equal to pi dOL. Overall heat transfer coefficient it being labeled as U. So this is the formula that we already know. Q dot equal to delta T over R is equal to U A delta T. Alright, this formula you could rewrite as 1 over UAS equal to 1 over UIAI equal to 1 over U naught E naught equal to R equal to because this is previous R, so you could see that the last slides, just bring the R over here. Okay. from the previous slide to here. So we have the R is going there. Okay. Okay, for example, this formula, right? We try to rewrite, so we get R equal to, because this delta t and delta t is being cancelled, so we got R equal to 1 over U E. Okay, U is overall heat transfer coefficient, A is the area. So here, for example, we have different AI, inner area and different AO. But for example, the AO and AI is much equally the same. Okay, so AO and AI is much equally the same. So we will get this formula. Okay, why? Because it's more equally the same numbers. If, for example, this is ln D, this is 1 ln 1 over 1, so 2 pi KL, we got ln 1 over 1 is equal to 0. Okay? 0 over 1, for example, is equal to 0. So we got, if this is 1, okay, whatever lah, over 10, so we got 0. And then okay, here you have an example of overall heat transfer coefficient for different type of heat exchanger. For example, water to water, you have U equal to 850 up to 1700. Alright, fouling factor. Fouling factor actually will affect the heat exchanger performance due to deteriorate rates with time as a result of accumulation of deposit on the heat transfer surface. So, for example, when you have a cylinder over here, from time to time, whatever debris bring by the fluids will stuck on the top of the inner side of the cylinder. So this one is fouling. The fouling factor actually will increase additional resistance to the heat transfer. Because of what? Because, for example, this is too many of fouling, so this will create an insulations. So it's hard for the heat to move from inside to outside or the other way. Okay, how to include the fouling factor in our calculation? Basically we just plus, if we have, for example, we have on the inner side, this is the inner side, okay, so we just plus RFI over EI. What is RFI? For example, this inside is refrigerant liquids. Okay, so we have this is refrigerant liquid, so we have RFI is equal to 0.002 over AI. On the other side, we have RFO over AO. For example, we have fouling outside of the wall, and this middle one is refrigerant and the outside one is water. So we have water over here, but water is so many. Just example, we have a 0.01. There we go for water. Let's plus these two, RFI over A or RFO over A. Okay, this is how we want to analyze heat transfer, heat exchanger. Okay, heat transfer in heat exchanger. So there are two methods that we could use. The first one is LMTD method. Second one is NTU method. So before I forgot, actually the fouling factor will increase when the operating temperature, the length of the service increase, and the fouling factor will decrease with velocity of the fluid. So fouling factor will not affect if the velocity of the fluid is increased. Okay, the next one is analysis of heat exchanger. It has two ways to calculate it. We have LMTD method, log mean temperature difference, and the other one is NTU method. So to calculate it, we will go the next chapter later on. Okay, thank you.